Right, you're all back again. So, welcome. Now, what I wanted to do in this lesson is really do a mixture of the 3062 and 3063. So, I don't know if you remember last time we looked at using the Ka value to calculate a pH of a weak acid solution. Were you all here for that? Or you remember it or not remember? Okay, that's right, April, you weren't there. Okay, so what we're going to do is I'm going to look at a titration because that'll cover just about everything, and we're going to do calculations at all those different points. So if you remember when you did a titration, you had, let me just get my ink tools, come on, there. You basically had your pipette and your burette, and if you then drew a graph, excuse my terrible drawing, but if I drew my graph with my volume along this end on the x-axis and my pH on the y-axis, do you think you're going to get a gradual change in pH like that? Is this, if you did the titration last year, is that what you expected, or did you sort of get a sudden color change where it sort of went from, if you did the phenolphthalein one, it was colorless, 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 and then it suddenly went pink, and then you added a few more drops and it was a dark pink. It was, yeah. So, April, it is gradual in the beginning, but then it actually changes. So, as if you'd done the titration, you would see it seems to not do anything, the color doesn't change, you know, the pink might appear and then disappear, and then you get the pink and you just have to add a few more drops and it suddenly goes from a very pale pink to very dark pink, and then the color doesn't change very much after that, it stays a dark pink. And that's because what more or less happens is if you say adding, you've got your base in the burette, so if that was your burette, and you've got your conical flask down here, okay, with your acid over here. Okay, right, so yes, so it does disappear until, as I say, you get to that pink when it doesn't disappear, and then a few drops will change it. So if I have the acid in the conical flask and I'm measuring the pH, you know, so I've got a little pH meter in here measuring it. Do you think I'm going to start off with a low pH or a high pH? A low pH, because it's acid, and acid has got a pH of, you know, less than 7. So if I had, say, something like a strong acid, so say I had HCl, and say it was a 0.1 mole per liter solution, you could actually work out what the pH is in that flask before I've added any base. My burette looks a bit weird, so let's make it having a little thing over there. So what would my pH be? And the equation you use is pH is equal to negative log of the hydronium ion concentration. So can anybody work that out? What would that be? 1, correct. Okay, because it's if you take the log of 0.1 and then you take the negative value, it'll end up, because it'll be -1, and then you multiply it by negative, you get a positive. Okay, so that you can only use this formula for a strong acid. You cannot use it, you cannot use it for a weak acid. And the reason being is when we say, if I have HCl and it's 0.1 molar or mole per liter, it will completely dissociate, so I can assume that my concentration of the hydronium ions is the same as my, you know, what I've said the acid is. So it's for strong acid only. So if I've got sort of pH of 1 sort of starting down here, it slowly increases as I add base, and then I'm going to get a sharp, not very good drawing, a sharp increase, and then it tails off again. April, the H3O plus, that is just the proton that's been donated. So an acidic solution will always have hydronium ions, and that comes from the acid that you've added to the water. So if I've added HCl, the HCl reacts with the water to form hydronium ions. And yep, so we're going to have a look at that. I'm just going to get, well, okay, that's removed everything. That doesn't help much. So it's a gradual change, sudden change, and this doesn't actually happen with pH. It actually also happens with temperature. You get a sudden peak at that temperature, and then it cools down again because these reactions are exothermic actually. But anyway, that's a digression. So what basically happens is, as I add my base, so if I say I'm going to be having HCl plus NaOH, that is going to react to form NaCl plus H2O. But hopefully you'll know enough by now that what's important is my H plus and my OH minus forming H2O. All these other ones here, whatever, you know, this is just the spectator ion. Okay, it's a salt that's neutral, it doesn't react further. So I can say my equation is just H plus OH minus, and that forms H2O. Now, this is actually also in equilibrium with the water. Okay, so as I'm adding in my OH, I'm not going to be getting much change overall. So it's the pH starts low because of the acid. I'm adding base. There is a slight increase, but we've got this whole sort of equilibrium until it's reached this point where you know, you've now added sufficient base, so it's going to make a big difference in the quantity of OH minus. And then what will happen? So, Johnny, when you've used up all the H plus, yep, there will always then be a little bit of H plus, even in the most basic solution. So even in a pH solution of 14, you'll have this tiny, tiny, tiny bit of H plus hydronium ions. So it's really because we're in this equilibrium with water, because remember, if water is in equilibrium with H plus and OH minus, but then when you've tipped it, that you've pretty much got used up all the most of the H plus, and you're adding more OH minus, it suddenly shoots up, and then you get back into that sort of thing where there's not much change again. I don't think I explained that very well. I'll think of another way of trying to explain that better. You can actually do these calculations, and there are four major points that you have to look at. The first one is the initial calculation. The next one is at the equivalence point. Now the equivalence point is sort of halfway up the steep graph. Just as a matter of interest to get the terminology correct, equivalence point is different to the end point, because you may have heard both those terms. Have you heard both those terms? Yep. Okay, so the end point, this is when there's a color change. So that's when your colorless solution turned pink, or your yellow turned blue, or the other way around. So your end point doesn't have to be when the solution is sort of being neutralized, because if you chose a wrong indicator, the color change will happen, you know, at its particular pH, and not necessarily when it's been neutralized. So this is just when there's been a color change. and you stop the titration, you end the titration. Equivalence point is where we've said all the acid has neutralized all the base. Okay, so if you like, it's your neutralization. And does not mean actually pH of 7 actually, but that is where all the acid you've added has neutralized all the base that was in that solution, or the other way around, base to acid. And you want, of course, to make those 2 points as similar as possible at a similar pH. Right, so that's the second point. Then normally we take 2 other points to calculate, and the other point is where we are halfway between these 2 points, and I'll explain that just now. And the other one is normally when we are double the amount. So if this took us, say, 10 mils to go from this point to that point, then we take it at, say, at 20 mils. So 10 mils plus 20 mils. So 10 mils plus 10 mils makes 20 mils. So those are the 4 points. So let's have a look, and I'm just going to tidy this up. And we're going to do the color changes. So we've done the first one. So we're going to the calculations. This is a strong acid, strong base one. So go back to here. Well, we can actually get rid of that one as well. So the first one we've already done. Because it's a strong acid, we can use the pH is equal to negative log of H plus. And if it was a 0.1 molar solution, it's a negative log of 0.1, and you'll get a pH of 1. So if you were drawing this graph, you would do it at a pH of 1. Now, let's actually add a few more values in here. So let's say we had 20 mils, because I'm trying to keep the calculations as simple as possible, 20 mils of a 0.1, that was very messy, 0.1 mol per liter HCl solution, and I'm titrating it with a 0.1 mol per liter NaOH solution, which is a strong base. So you will be always given the concentration of the acid or the base. I've only once seen it where they've done, you had to work out the concentration of the one. Normally it's level 2 where you've got to work out the concentration of an unknown one. Level 3, they give you both concentrations and volumes, and you just have to, because you always get given a weak acid or a weak base, something like that, a bit more complicated. I'm just starting with a more simple one, which is a strong acid, strong base. So that was our first point. Now, halfway, if we've got 20 mils of 0.1, then we halfway will be, what do you think? How much acid, how much base must I add to my acid to get halfway to the equivalence point? 10. Okay, you said mils, 10 mils, right. So at 10 mils, what has happened? So first of all, think of your total volume. What volume have you got in your conical flask? If you think of my original sketch, I had, yep, 30. Well done. Okay, so I've now got 30 milliliters. Okay, it was the original 20 of the acid plus the 10 mol of base. So at 10 moles of NaOH being added. Right. I've had half my acid reacted. So what is my amount of acid left? So NHCl okay, is going to be equal to what? To this again now. We have to work out our concentration of hydronium ions. At this point, halfway point, do we have more acid, more base, or equal amounts of acid and base? We actually do have more acid. So Caleb, if you think about my beaker or my conical flask with my burette coming in, I've only added 10 mils of base and I had 20 mils of acid, and I've got the same concentration of acid and base. So at the 10 mil point, I've added, so if C is equal to N over V, so N is equal to C times V. Okay, so it's going to be 0.1 times the volume. We had originally 20 times 10 to the minus 3. That's to convert, the times 10 to the minus 3 is to convert milliliters to liters. So that's the point of this bit over there. And so you should come up with an answer of something like do you get 2.0 times 10 to the minus 3 mole? Yep, okay, great. And the N for the NaOH is going to be C times V, and it's also going to be 0.1, but it's times 10 milliliters. So to convert, yep, so we're just doing the straightforward acid reacting with the base. Yep, okay. And you are correct that at that point you've got equal amounts of conjugate acid to the base. Right, so we've got this times 10 to the minus 3 to convert to liters, so that's going to be 1.0 times 10 to the minus 3 mole. Okay, now our base, being a strong base, is going to react completely with my strong acid. So I'm going to be, so all of this is going to react, that I've got nothing left. So if I had 2 times 10 to the minus 3 of acid, and it reacts with 1 of the base times 10 to the minus 3, I hope you can all see that after that reaction at the halfway point, the NaCl is going to be equal to the 2 times 10 to the minus 3 subtract 1 times 10 to the minus 3, because that's the bit that's reacted with the base, and I'm going to be left with 1 times 10 to the minus 3 mole. Right, so to work out my concentration of HCl, it's going to be then C is equal to N over V, so it's going to be 1 times 10 to the minus 3 all over my new volume of 30 milliliters, which is 30 times 10 to the minus 3. At achieved level, I don't think they're too fussy about having the times 10 to the minus 3, but certainly at excellence, and I think at merit as well, always use liters. So convert all your milliliters to liters. Okay, and you should get an answer of, if I just work it, do you get an answer of 0.0333 recurring? Yep. So that's your concentration. Now, if that's a concentration of HCl, what can you say about my concentration of hydronium ions? Would it be the same? Yep, because it's a strong acid. You can only say that for a strong acid. That's why you can see it's going to be more complicated for weak acids. So I can say that it's 0.0333 recurring moles per liter for that, And so if I wanted to work out the pH, and I'll just let me just bring this down a bit. So the pH at this point, 10 milliliters, then it's going to be the negative log of that. And take my log. Do you get 1.47 or 1.48? Yep. Now remember, pH has got no units, and always do pH to 2 decimal places. If you're doing scholarship, then learn the proper way with significant figures, because actually this here is just a placeholder. It's like those zeros before a value, like 0,0. Okay, so it's just that. So this is basically telling you it's got 1 0 over there. Okay, so it's just a placeholder, and the 4/8 is actually the significant figures. So if you're doing scholarship, use 3 significant figures. You would have said 477. If you're writing the NCA exam, use 2 decimal places, because there's always this constant battle in chemistry teachers about what constitutes a significant figure or not. Yep, so in scholarship you would say that, because they want the proper stuff. In the exam, don't do that, because one year I know they knocked you back even though you were correct. So it caused a bit of an issue, but I think always just make it to 2 decimal places. Okay, right, so that is, and so you can see it's 1.48. It hasn't gone up very much, has it? So if this was a pH of 1, after 10 mils, we're only at 1.5, pretty much, 1.5. So it's not very much. Now we go all the way to the 20, and I'm afraid I'm going to have to just rub out here. Let me just do it the quick way. Come on, select objects. It's not working. So I'll just rub it the normal way. Okay, well, while I'm rubbing, we can work out, we're now at the equivalence point, so we have added exactly the same amount of base to the acid, so we've added 20 moles. So what can you tell me about the pH? This one, for a strong acid, strong base, you don't even have to do a calculation. It's a pH of 7. So if you have a strong acid, strong base, then you get a neutral salt, or as you can see from this reaction, you get water. Water has got a pH of 7 if it's pure water, so you don't even have to do the calculation. You can just look for 7 on your pH thing after 20 mils. So remember, make this now. That was 10 mils, so this is 20 mils. You can just draw the 7. You don't even have to do the calculation. You just simply say H plus is equal to OH minus, and so pH is equal to 7. But I will say I've never seen an exam paper where they give you a strong acid, strong base titration and ask you to do the calculation. So there could always be a first time, because it is in the curriculum. So that is point number 3. Now the 4th point is where we've added, so if it was 20 mils, is where we've now added 40 mils of base. So if we've added 40 mils of base and we had 20 mils of acid, what is my total volume? 60 mils. And remember, you convert that to liters. So of that 40 mils of base, I think you can sort of see 20 mils have been used up with the acid. So I've only got 20 mils of base to really think about. So We've now done the H plus, so now we're looking at the OH minus, because we're saying we've had 0.1 mole per liter of base times the 20 mils, and of course we've got to convert it, so let me actually do it straight away to liters. So if I wanted to get the number of moles of OH minus, N is equal to C times V. So that is going to be, again, we get back to 2 times 10 to the minus 3. Now I've been a bit slack in the number of significant figures as such, but that's because I've just been using this to one significant figure here. In the exam, they will give you the values to 3 significant figures, so always make sure throughout your calculation you never give less than 3 significant figures, and then at the end make sure your answer is 3 significant figures, is 3 significant figures. Yep, so April, they should always give it to 3 significant figures, or if they've given 1 to 4 significant figures, the other one will be at 3, so, because you always take the least, the smallest number of significant figures. And of course I'm talking about measured values, so not stoichiometric ratios of 2 acids to 1 base or something like that. That 2 doesn't mean it's a 1 significant figure, because that's just a multiplication number. It's not a measurement. Okay, so we've got that number of mole. So to work out my concentration of OH minus, remember the square brackets means concentration, that's going to be N over V, so it's going to be 2 times 10 to the minus 3. Now remember what my new volume is. So it's 60 times 10 to the minus 3, and so we get 0.0333 again. So you'll find these sort of things, numbers start tending to come up all the time, because sometimes they're sneaky and they give you 0.1 and 0.2, and then you won't get these exact values that I've got. But if they give you always 0.1, 0.1, you know you're going to get that. So what I do now is I can work out the pOH. And the reason why I can do that is because the pOH is simply the negative log of the OH minus concentration, just like the pH was the negative log of the H plus concentration. Okay. The reason why I work out the pOH is I can find out the pH from this equation. And that comes about because really from this equation, let me give it a different color. Remember, water is always in equilibrium with its ions, so I could change that to equilibrium arrows. And the amount that's dissociated, this is always 10 to the minus 7 in the neutral solution, and 10 to a minus 7 for the acid in a neutral solution. As I add more base, then I'm going to get less acid. If you like, it's like that Le Chatelier. If I'm adding more base, it's going to be shifting towards the right to give more water, which means that my acid is going to decrease. Or if I add more acid, then my OH gets less. But if I multiply these two together, I will always get 10 to the minus 14. And that equilibrium constant is Kw. The W just stands for water, and the K is the equilibrium constant, because water is in equilibrium with those ions. Not very much is dissociated. It's a very, very tiny amount. Okay, but knowing that equilibrium constant 10 to the minus 14, that's where if we take a log of all of those, that's where that comes from. So if I work out now the pH, the pOH of that, so where's log? you get 1.47 or 48 again. Okay, but that's the pOH. So to work out the pH, it's going to be 14 subtract the pOH. So you're going to get 12.52. So does that make sense? I know I've gone through that quite quickly about where that 14 comes from, but I think if you just learn how to use it, then that'll be fine. But it's actually all to do with that equilibrium. So your final point over here should be done at 20 mils, and this should be between 13 and 12, because it's 12.52. Sorry, 40. 20, you are right, 40 mils. Thank you very much for pointing that out, because it's 20 plus 20. Now, why, if I had the 0.1 sodium hydroxide, you should know that the pH of a 0.1 mole per liter sodium hydroxide solution should be a pH of 13. So why is not my pH of 13 over here? Why is it less than 13? So just while you're answering that, I'm just reading Johnny's. Yep, so Johnny, you can do that way. I always like doing the pOH and then say 14 minus, but you can always do it in the other way. Yep, okay, if you don't like logs, I prefer that way. So, not so much the dissociation of water, Caleb. What basically happens is if you had pure solution of sodium hydroxide, in other words, your original one that was still in your beaker that you added to your burette, that has got a pH of 13. But because you've added it to my conical flask that has some acid, can you see that 20 mils in that acid has diluted my base, so it has dropped the pH. So in spite of all my acid being reacted, that extra volume has diluted the base, and that's why it's not quite 13. Okay, so that is your those are your 4 points that you always use to draw a titration curve, and you could be asked to draw a titration curve. So what I'm going to do now is, because that's the so-called easy one, the strong acid, strong base. If you have a weak acid, strong base, you will never, by the way, be asked a weak acid, weak base. You can do it, but it's going to be incredibly complicated because there are so many equilibria, you can't make your normal assumptions and so on. So you only have to do strong acid, strong base, weak acid, strong base, and weak base, strong acid. So if I have this, here's my titration graph, and if you can imagine, I've now got my, I'm just going to keep it to acid in here. There is, of course, a variation where they put the base in there and you're adding acid, and then you start at the top. What happens here for a weak acid, strong base, is you've got a similar curve, sort of flattish, and then quickly steep, and then flattish again, but there are some differences. So first of all, you don't start at pH of 1. You'll always start at a higher level. Secondly, it's not sort of a gentle curve, sort of line going up. For a weak acid, you'll always have the sudden increase before it flattens out, and it never sort of flattens out quite the same amount. Then you get the steep incline as per normal, and then you get it flat again. And where it goes flat again, because you got strong base, this is again going to be between the 12 and the 13, like we did in the previous one. because the calculation is going to be exactly the same for point number 4 as we did just now. Okay, because all the acid, doesn't matter if it was weak or strong, all the acid is reacted, so we're only dealing with the strong base left. So we've done already point number 4. So let's look at point number 1. Okay, I said, remember, it's got a pH of bigger than 1. So let's give you some values. So let's say it was again 0.1, and we can say it's a weak acid. We'll just call it HA, and we'll give it a Ka. And as I say, the common one for ethanoic acid is 1.8 times 10 to the minus 5. It comes up so often you start remembering it off by heart. So why this is important, this Ka, is I can't say now 0.1 HA is 0.1 H3O plus. I can't say that because most of my acid is going to remain as HA, and not very much of it is going to form H3O plus. So when you get given a weak acid, you do that same thing what I did before, you know, the EEC method. Okay, equation, the expression, and then the calculation. So when you do the equation, you say, okay, I've got my acid HA in there. So HA plus water gives me H3O plus A minus. Okay, that's the reaction of a weak acid with water. It hydrolyzes with water. Most of it stays at HA, some of it forms A minus, and some of it, you know, and of course equal amounts of A minus to H3O plus. April, HA, I'm just giving it as a symbol for a weak acid, and I've just sort of picked this Ka for it. I could have called this ethanoic acid, but it's just to keep things easy, so I don't have to write CH3COO minus and CH3COOH. So it's really just, and you'll find often in an exam they'll say that, you know, they'll say butanoic acid, and then they'll say H-but, or propanoic acid, you know, H-prop. So it's just a way of shortening it to make it easier to use in a calculation. So just give whatever shorthand they use. So I'm just calling it HA. So A minus is the anion, and H3O plus is the hydronium ion that's released, and HA is the weak acid, of which most of it is sitting in water as HA. And of course, as you're adding base, this is reacting. So by Le Chatelier, you know, the HA is going to keep on dissociating until all the HA has been used up in the reaction. So during the titration, you know, it is shifting towards the right, and so it is being used up and it is being neutralized. So that's the equation. The next one is to do the expression. Now the expression is, remember, always the multiplication of the products over the reactants. So the products are what's on the right hand side. So it's H3O plus and A minus, over the reactants, what's on the left hand side. Now I don't put in water because water is a liquid, and the concentration of a liquid does not change unless you change the temperature. And remember what I said, equilibrium constants are only a constant at a particular temperature. If you change the temperature, the value will change. So that has been included in here, and we call it Ka for acid. Now, one way of sort of spotting this, if you see an A, then you must have that in the equation. So if I'm going slightly changing, you know, things, if you were, say, given ammonia and you wrote ammonia, no, let me do, okay, yeah, sorry, let me just do it, ammonia. If I reacted ammonia with water, so I'm going to get NH4, because it's a base, it's a proton acceptor. So it's accepted a proton, so you remember the positive. Please make sure you write your charges in. Can I say, if I write this expression of NH4 plus OH minus all over NH3, remember it's just my products multiplied together divided by my reactants, is this a Ka? It's a Kb. It's not a Ka because I don't have H3O plus, I have OH minus. So if you see OH minus in your equation, then the expression you build up on it is the Kb and not the Ka. If you see the hydronium ion in the equation, then it's a Ka. The other thing where students sometimes go wrong is, say they get given, because what we're going to be getting here is a salt being formed. So let's just say it was ammonium chloride. It doesn't really apply to this. But if students think of ammonium chloride and they go, okay, ammonium chloride, and it reacts with water, and so I'm going to get NH4 plus Cl minus, and they go, that's the equation. And by the way, always give states. Okay, so I must admit I've left it out, but so always give states. And then they'll go, right, there's my equation, so I'm going to say K is equal to NH4 plus Cl minus all over NH4Cl. And they go, right, I've been given the Ka, so I'm going to call that the Ka, and I'm going to carry on with my calculation. Is that correct? Is that an equation where I can write a Ka? No, I can't write a Ka because I don't have any hydronium ions there. You've got to have a hydronium ion. So always use that as a check to see if you can use your K expression. If you don't have a hydronium ion, then you haven't got a Ka. So you can't use the given Ka value. So that's just a common error students do use, that they'll just pick on any equation and they'll just go say, okay, Ka has been given, I'm going to use that value in my calculation. And of course, it's going to be totally wrong. You can only use Ka if your expression has a H3O plus in it. Right, so that's going to just rub all that out. So now we're going to go and we're going to work this out. So we say 1.8 times 10 to the minus 5, which is the Ka, is equal to. Now, I can do assumptions to make it easier. Because remember I said you're only given a weak acid, strong base. You're never given a weak acid, weak base, because you can't make your assumptions. Here I can make assumptions that because HA is a weak acid, most of it is going to stay as HA. So if I've been given 0.1 molar HA, most of it is going to be HA, so I can call that 0.1 down here. We know from my equation my HA reacts with water to form hydronium ions and the anion. And for every one hydronium ion, I form the anion. So can you see I can also make the assumption that my concentration of the A minus is the same as the concentration of the ammonia, of the hydronium. Okay. I know we do have hydronium from the dissociation of water, that's always there, but that is very, very tiny. So that's why it's an assumption and not a fact. We can't say that these are absolutely equal, because remember, I've always in the background got my water in equilibrium with my ions. Okay. So that's always happening in the background. But that's such a small thing. I mean, the Kw is 10 to the minus 14. So, that's 10 to the minus 14. That's 10 to the minus 5. This is many, many, many orders of magnitude smaller. So we can make that assumption. Now always, yes, it's negligible. So always write those assumptions. So you always say somewhere, either on the one space or, below it or above it or somewhere. So always say, your two assumptions. So you assume that the HA is equal to 0.1 mole per liter, because we know some of it has dissociated, so it's not exactly 0.1, but we can say 10 to the minus 5 is small enough that hardly anything is actually dissociated, and we can assume that H3O plus is equal to the A minus. Okay, so what we've got here is just simply H3O plus squared. Okay, so 1.8 to then divide by 2. Okay, I'm not quite sure divide by 2 because we've got to square it. Yep, the square root. Okay, correct. So now what I suggest you always do is this one is at the bottom over here. So it obviously goes to the top on the other side. So it's 1.8 times 10 to the minus 5. So that didn't come out. Times 0.1 is equal to H3O plus squared. Now, I suggest always work this bit out in your calculator first, so that, because I find if people try and do all the things at once, unless you've got a fancy calculator that you really know well, that's where the errors start coming in. Because you might have taken the square root before you actually multiplied by 0.1, for instance, or something like that. So get that value first, and then take the square root of it to get the hydronium ion concentration. So this would be 1.8 times 10 to the minus 6 now, if I multiplied those two together. And so you take the square root of that, rather than the square root of 1.8 times 10 to the minus 5 times 0.1, because invariably an error comes in. So if you have that, you should get square root. Did you get 1.34 times 10 to the minus 3? Yep, okay, great. And so then you'd get your pH, so you just take a log of that, and looking for my log. So I get a log value, and then I take the negative of it, so the pH is equal to 2.87. So you can see this value here is 2.87, unlike the 1 I had for the strong acid. Okay. So please, by the way, do you notice how I've written H3O plus there? I had the square over here, I had just the concentration, then I had the pH. A common error is, where people say this and they'll say equals, and they don't put this in. So it sounds as though H3O plus squared is equal to 2.87. Can you see that that is not good? They would accept it for achieved, okay, because you obviously know what you're doing. You were just sloppy, but you certainly wouldn't get excellence with that. So, always state what you are doing. And you must show working for excellence. So you can't just say, well, I'm doing it all on my fancy calculator. So, from the step here, I can just say pH is equal to 2.87 and everybody's going to be happy. They're going to say, where's your working? Okay, so they'll even at achieved allow those sort of things to go through, but not at higher levels. Okay, so we've done that one, and we've done 0.1 and we've done 0.4, because as I said, 0.4 is exactly the same as what we did previously. So point number 2 now. So this is when we've added 10 mils of my base. So we have to do exactly the same thing as we did. I've rubbed it off now, unfortunately. But can you see the amount of acid I've got left now at the halfway point is going to be really 0.05 of acid. Okay, because half of it is reacted and the other half is around, and it's going to be in 30 milliliters. Tell me if I'm going too fast, because once you've done these so many times, you tend to take all these shortcuts. But just like I did the previous time, you could say my N in the beginning of my weak acid. Sorry, that should have been a... Oops, what happened? There. So my N was, N is equal to C times V, so it's going to be 0.1 times 20 mils, and then you convert it times 10 to the minus 3 to get to liters, and then you work out the N OH minus that you've added, which is C times V, which is 0.1 times 10 to the minus 3, and then you work out that you've got half of it left. Okay, Joe, how do you know that it's 10 mils? Because, okay, I'm going to be using exactly the same figures of, I've got 20 mils of acid. The concentration of the acid is 0.1 mol per liter. Okay, the concentration of the base is 0.1 mol per liter. So let's say sodium hydroxide or whatever it is. Those are typical measurement points, and they've often come up in the exams like that, but as I say, they don't always come up like that. Sometimes they'll make this 0.2 compared to 0.1, or they might give arbitrary values. They'll give, say, this is 0.156 moles per liter. And then, you follow the same sort of thing. You work out then how much is reacted, and you subtract. It's just, you can't do it in your head anymore. Then you have to use your calculator. So like I did this in my head where, because this is going to be equal to 2 times 10 to the minus 3, this is going to be equal to 1 times 10 to the minus 3, so my N HA left over, because is going to be 2 times 10 to the minus 3 subtract 1 times 10 to the minus 3. So if they give you funny values, you still work it out the same way. It's just then this value won't be a nice round 0.1 anymore that you can't do in your head. Okay, Joe, it's going to be neutral at 40. No, we're using 20 mils of HA, and because our base and our acid is exactly the same, then, oops, I should put a minus there, we're going to need 20 moles of base to neutralize the 20 moles of acid. Does that make sense? 40 moles is when I've added. Okay, can you see the number of moles of 20 moles of acid is 2 times 10 to the minus 3. No, it doesn't matter. A titration, doesn't matter if it's a weak acid or a strong acid for the actual titration sort of thing. Because remember what I said, if this is an equilibrium, the HA reacting with H2O to form the hydronium ions in the A minus. So it is an equilibrium, so it mainly stays as this. But as I react by Le Chatelier, as I react the hydronium ion with my base to form water, how is this equilibrium position going to shift? Which way is it going to go? Towards the right, towards the left, or nothing? Towards the right. So what's going to happen as I keep on adding base, this equilibrium position is going to keep on shifting to the right. So I'm going to get less and less of HA because I'm forming more hydronium ions to replace the stuff that's being removed. Okay? Because I'm removing it by reacting it with OH minus. And it's going to do that until all my HA has reacted. And when all my HA has reacted, then, all my molds have been used up, and then it's my neutralized solution, which won't actually have a pH of 7 actually. Okay, so that is an important point to grasp, that a weak acid and a weak base will still be titrated to completion as long as I'm reacting it with a strong. So a weak base with a strong acid, or a weak acid with a strong base. You won't get weak acid, weak base, because that's just going to be too complicated. Okay. Yeah, if you do a weak acid, weak base, it's going to depend on the Ka values and Kb values of each one, and it'll be sort of somewhere in between. It'll be a merry mess. So you'll never do a titration. That would be a dumb thing to do, because you're not actually going to get a proper solution. Okay, it is 4 o'clock, so I was actually hoping to finish at least one of these. So next time I'll start off with these 2 points, and then we'll do the weak base, strong acid, and then buffers. And then it's, you've done all the calculations and whatever that you need. Okay, right. You have a good time.